if you have any question, you can ask me anytime. Okay? You can stop me and ask the question all the time. I'm going to hide the floating meeting control. Okay. Okay, as I mentioned, we will continue about the technique of transmission, which is the spread spectrum technique. Okay, before we starting to understand the concept of direct sequence, let's recap a little bit about the concept of spread spectrum. Okay, why do we need the spread spectrum technology? Any of you still remember, right? Why we need the spread spectrum? Because in the environment, I mean, when you transmit the signal wirelessly, okay, there's many cause of impairment. It can be noise in the hardware, or it can be distortion or attenuation from the distance, right? When user move away from the transmitter, so the signal strength or power decrease, right? And moreover, there are a kind of multi-part signal received at the receiver. Okay, there are two cases of impairment of the multiple received signal arrive at the receiver, right? One we call interference, and another one we call multi-part fading. These two phenomena have co-concept of the multiple receive signal, right? What the difference among these two? Can any of you share to your friends? What's the difference between interference and multi-part fading? Can any of you share? Maybe Tawinwit? What's the difference between interference and multi-part fading? Or maybe, oh, help me. What's the difference? Maybe up? Is up here? I just want to make sure that I'm not alone in the class. Maybe Dan, can you help? What the difference between interference and multi-part fading?
Multi-part is like when the same sorts of transmission just reflect or scatter with another object and arrive at the receiver like with a little bit of delay, so sometimes it cancel out. But interference, it's like it is another transmission with the same same frequency, so it like collide with each other.
Yeah, thank you, Kan. Right, that's correct. So this figure represent the multi-part fading, as Kan explained. So in this case, we have only one transmitter, right? And actually, when the transmitter transmit the signal, actually is the wave, right? Is the wave. So actually, what we expect is that we can receive the direct part, which is this one. Okay, this one. We need this one. But you know, the wave front can imping or incident with other building and then go to the receiver later on. So it means that in this phenomenon, we have only one transmitter, transmit only one signal. But anyway, the receiver can receive one shortest distance signal, and later it can receive the delay, as Kan mentioned. So it can receive multiple signal at the receiver side. So the disadvantage things that we receive multiple signal is that sometimes it gain, right? It plus to it combine to each other, and then the power increase. But sometimes the powers like deduct from each other. So this kind of multi-path receive signal can make the receive signal fluctuate a lot. Fluctuate means that when you consider in time domain, sometimes you can have a big power, but suddenly for the short period of time, it like have very low power. It's like this. So in the channel, when we face with this situation, it's kind of very difficult to detect the prospective or the required or the desired signal. Okay, so this is the phenomenon of the multi-path fading. All right, we have only one transmitter. Fading means that it like deduct to each other and then it's like reach to very low power. And for interference, if you take a look at the receiver side, you can see many signal also, but the difference of the multi-path fading and interference is that you have only any transmitter, say transmitter 2, and you as a receiver can receive the signal from other sources, say transmitter 2 as well. And then when you take a look signal, it kind of combine or deduct to each other as well. So it fluctuates also. I mean, the signal is fluctuated. This is no good for the received signal that, it's very difficult to detect what is the desired signal. Okay, so, but we cannot avoid this one, right? We cannot avoid the obstacle in between transmitter and receiver. And then in the real scenario, there's many transmitter also. So we cannot avoid these two situations. But as an engineer or the researcher, you have to think about how we can maintain or improve the received signal with this scenario. And I explained last time that one of the technique is that we can use the spread spectrum technique to achieve the better, quality of the signal. Okay, and another technique called OFDM. This one I will teach you next week. Okay, so this is used a lot in licensed wireless and IoT application. All right, and then this is the signal in frequency domain, how the signal look like. For the spread spectrum, what you have to do in the transmitter side before you send the signal is that you have to make a bandwidth of the transmitted signal bigger than just the narrow band, right? Because of what? You still remember, right? So this is a situation before we use the spread spectrum, so this can happen. Okay, give me. Okay, so for this one, interference, also the signal, right? And this is the desired signal. When we take a look in frequency domain, right? The bandwidth are very similar. In the unit of some few kilohertz. Okay, the bandwidth of the interference and the bandwidth of the narrow band signal are very similar. So in some cases, when you transmit a signal, maybe the bandwidth of the signal and the bandwidth of interference just coincide with each other like this. Accidentally have the same bandwidth. So what you get from here, from this figure, is that at the receiver side, you can have like lower SNR, right? So SNR is used for estimating the efficiency of the receiver. If the receiver have a high value of SNR, that would be good, right? Because the definition of SNR is that it is a power of what? Desired signal, okay? And the power of the, say here in this case, interference, or it can be noise or multipath fading signal also. So it means that if the power of, you have effect with this one, if this is big, so it means that the ratio become lower, right? So this is not good for the communication part. So what can we do? How we can avoid this situation? So this is, I just explained, right? We can get the low SNR if we face with the interference with the exactly same of the center of frequency and the bandwidth, right? So what can we do is that, okay, we can make the transmitted signal having a much larger bandwidth, okay? So this is called spread spectrum transmission. So if you compare between these two, for the transmitter side, it seems that, okay, the power of the signal is lower, but suddenly at the receiving side, okay, so this is just the duplicate slide as I already teach you. Okay, this is the receiving side. When you observe the signal at the receiving side, so you do reverse process, right? For interference, you try to make it. So actually this one come together. So this is the signal from the medium, right? From the medium, from the air, arrive as the receiver. Then the receiver, after receive these two signal, it will do the reverse process. So it means that it have to make the wider signal become like shrink as it should be. And then this signal will be done with the same process. So it means that because this is the first time of the interference to do the spreading, then for the receiving side, it seems like the desired signal gets shrink as it should be from the transmitter, but suddenly the bandwidth of the interference is large. And then when you observe the value of SNR, so you can see that this is the power of the desired signal, right? And then this is the power of kind of noise. So it means that the receive SNR, okay, receive SNR become larger. So if you compare two systems with and without in spread spectrum technique, you can say that you can get an improved SNR by using the technique of the spread spectrum. All right, this is a concept of the spread spectrum. And before midterm exam, I teach you one technique called frequency hopping spread spectrum. Okay, what can we do with the frequency hopping is that, okay, we have a bandwidth of signal already modulated with FC. This is carrier frequency, right? And then when, okay, say this is time domain and this is frequency domain, right? And then actually, when you want to transmit the signal, there are kind of data sequence, right, with modulate with the same carrier frequency. But when you transmit the signal using the frequency hopping spread spectrum, you will send a signal as a package, right? Say, for example, this package number 1, number 2, number 3, number 4, and each packet will jump to the frequency that have been assigned before at the transmitter side. Okay, say for example, if already modulate with FC, then the frequency shift pattern can be like 4, 2, 1, 3. So if it land on like this, the package will be sent to the different frequency, right? Example here, package number 1 will send to frequency 4. And then package number 2 will send to another frequency. So this is not good. Okay, I will erase to make it more correct. So the frequency become 4 as well in this example. So this is F1, F2, F3, and F4. So if package number 1 will be sent, it will be jump or hop into frequency F4. So the package will be here. And then for the next package, when the time change, and then the package number 2's turn, and the frequency become F2. So it would be like this, right? Package number 2. And then it turns off package number 3, right? And the frequency is F1. So it's like this. And package number 4, it will jump to frequency number 3, like this, right? And so on. If you still have the data sequence, so you will jump from F4, F2, F1, and F3. So if you compare traditional system without the spread spectrum, you will just only use this bandwidth, right? Only one bandwidth of the carrier frequency. But when you jump or hop like this, the bandwidth become 4 times, right? 4 times of the original or narrow band system. So this is one of the technique that can make the bandwidth larger compared to the traditional system. So you can see here that the signal it as is. What I mean is that when you want to transmit, for example, if you take a look in a sequence like this, and then actually what we send in the air is not this one, right? We send the signal as the electric signal. For example, if one is positive of the voltage, right? If this voltage, and then maybe -1 represent with 0 and so on, right? And then, so what I mean is that by using the frequency hopping, we do not modify the shape of the signal. The shape of the signal is still as is, and then modulate with the carrier frequency and send through the air. Okay, this is what frequency hopping does. Okay, the system will send the original signal by modulating with the carrier frequency, and then before sending it have a block diagram called like to assign the frequency hop, right, and then propagate into the air. So what I mean is that this is still be like this as is. But if you take a look, another technique we call direct sequence spread spectrum, the process is different. But the concept of making wider bandwidth is the same. I mean, it tried to make the spectrum wider, or to make the bandwidth of the transmitted signal wider, but the way it does is different between two techniques. Okay, let's take a look here. So this is the general concept of the communication, right? In the transmitter side, okay, we have a source to generate the information that you want to send. And then you have to modify the signal. You have to modify, not the signal. Actually, this is the data for the information, right? You have to prepare your information or data to be suitable for transmission or prepare for propagate into the air. So what you need is to make the data to be a signal, right? In chapter 2 or chapter 3, we learned this already. We have a signal, and then the digital signal with very low frequency cannot be sent as is into the air. What you need is modulator, right? You understand already. You modulate the original signal with the high frequency of the sine wave, we call carrier frequency. And then, okay, before we transmit, we need to make it strong. You need the amplifier, and then you need the antenna if it's wireless channel. That is the basic concept of the communication theory. But if you need to add the step of the spectrum, you need one more block diagram, which is called spreader. So where should it be? It depends on what technique you are going to use. So for this technique, I mean frequency hopping. Okay, so you have a signal, you modulate already. So the block diagram of, the spreader of the frequency hopping will be here. So it modulates already, and then you just jump the package within the predefined frequency pattern. Okay, but for direct sequence, what you have to do is add the spreader here. Before the modulator. So what I mean is that you need to modify the data to be something before go to the modulator. Okay, so this step is called spreader. This one will make the bandwidth of the signal wider. Okay, it's not just jump to make a spectrum wider, but it modifying a signal before doing the modulation. Okay, let's see. So for direct sequence phase spectrum, there are two stage process also. Okay, what I mean is that, okay, it have the spreader here before doing the transmit traditional modulation. So here it can be ASK, FSK, PSK, and can be some number, okay? And it can be QPSK, and so, or can be QAM. So this one is a kind of the digital modulation technique that you already learned for especially these three, all right? Then before having the modulation, what you have to do is here, okay? So this is the data you have. Say that, okay, this is bit 1 represented by positive voltage, okay, and then it is an input of this block diagram, and take a look the output of the spreader. This is the output of this one. So in this stage, it already mentioned that the bandwidth is wide there. This chip, this signal have the bandwidth which is wider than the original data bit. Can you explain why? Why the bandwidth of the output like this is wider than the input signal? Any idea? So you see this is time domain, okay? Time domain represent the time duration that you send the signal with some voltage, right? And then the output in time domain, you can see that it's not only one wide bit, but it contains several smaller pulse, or you can say several smaller duration of bits also. For example, this is one symbol. This is one period of time. But if you take a look here, it's called each smaller part as a chip. Okay. If you take a look at time duration of the chip, we call TC. Time duration that you send one chip, which is very small, or take a short time for transmit one chip. So TC is much smaller than TH. And this leads to bandwidth of the chip is much wider than the bandwidth of the symbol. Do you have any idea why it concludes like that? Okay. Any idea? No? Okay, let's see. Okay, so let's see for each side of transmission. This is the transmitter side. Okay, it's just the duplicate figure here. Okay, it just focus on the transmitter part here. So in the first stage, each transmitted information bits is spread or mapped into n smaller pulses, and these smaller pulses and these smaller pulses called chips. Okay, so if you take a look this one, this is a 1 bit, right? And this is the smaller pulse, and here each pulse here called chips. Okay, if you take a look in this picture, I'm not sure if this maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe 11. So maybe this contain 11 chips, represent only 1 bit. All right, and then this chip will be the input of the modulation. So it means that instead of modulated this original data bit with the carrier frequency, you need to send this one to be modulated with the carrier. Okay, by using the digital modulator, and then you propagate. You propagate by using the antenna. Okay, all right. So why the bandwidth of the chip is wider than the bandwidth of the original signal? Let's take a look here. This is a basic concept, right? The bandwidth of any digital system is inversely proportional to the duration of the transmitted pulse or the symbol. Or to say, actually bandwidth is a frequency, right? I can say that, okay, bandwidth actually is the frequency is inversely proportional. Inversely proportional to what? To the duration. Duration means the time duration of the transmitted pulse. So if you have one symbol, as I represent previously, when you send one, the sequence of the signal, like this is symbol 1. If this binary, one symbol represent 1 bit, right? So in this case, the sequence of the data will be 1, 0, 1, 1. And one symbol takes TH. This is the symbol duration. Okay, this is time domain. But if you consider this signal into frequency domain, you can use the Fourier transform to make it like, okay, it represent this square wave. It can be like sinc function, and then you can consider that this one as a bandwidth. Okay, so it mentioned here that bandwidth is inversely proportional to the symbol duration, right? And then if the time is smaller, say this is smaller, what happened? The bandwidth become bigger, right? The value become bigger if the time duration is smaller. So if you see here, from here, TH is kind of large compared to the time that you send only one chip, right? So by using this relation, you can easily imagine that the bandwidth of the chip first is inversely proportional to the duration of the chip. And then if you compare TC and TS, this TC is much lower, right? So it makes the bandwidth wider. This is a very simple concept. Just make original time duration of the symbol become very short duration before transmitted. So that can make the bandwidth wider already. You do not need to jump like frequency hopping, okay? By using only first stage, the bandwidth already large, okay? Bandwidth is already large, and then you can do the process by using this one. I mean, this signal modulated with the carrier, and then you send it. So it means that you need only one frequency of the carrier to modulate your signal or the chips. All right, because the transmitted chips are n times narrower than the data bits, the bandwidth of the transmitted direct sequence signal is n times larger than traditional system without spreading. So what it means here is that if, example, maybe better to explain using this page, okay? So for example, I draw here that this is the original data sequence that you need to send without spreading, without direct sequence spread spectrum. And as I mentioned earlier, bandwidth of this one, the digital system is inversely proportional to the duration of the transmitted pulse or symbol, right? And then, okay, so if we use the green one as a code will be the one that that convert the original data sequence to be a chip. If we use this code, in which is represent one symbol to be a two chips. So it means if in this case, there are two chips represent one bit like this. So what the code do is just like do the multiplication. You can see easily here that, okay, this is the voltage of the signal 5 volt represent bit 1 and minus 5 volt represent bit 0. And your data sequence will be 1, 1, 0, 1, 0, right? And you apply the code with this is called, you can say that this is 2 volt peak to peak. Okay, 2 volt peak to peak means that from the maximum to minimum value, the difference are 2 volt. So you can say that this is 2 volt peak to peak. And in the same manner, you can say that this is 10 volt peak to peak as well. This is the same meaning as the data sequence is 5 volt for 1 bit and minus 5 volt in represents 0 bit. Okay, come back. Then after we have the original data multiplied with the code, so you just do the multiplication. Okay, 5 volt multiplied with 1 here, it will be 5, right? And this is 1 times or multiplied by minus 1, it will be minus 5 and 5 represent what? Represent just only bit 1. Okay. Sorry. Okay, and then if, for example, this is bit 1 also, bit 1 multiplied with the code, it will be 5 and minus 5. And then if it bit 0, in which represented by minus 5 volt times the code. So this is minus 5 times 1 and minus 1. So it will be minus 5 and plus 5, right? And so on. And then here is the signal that you have to send to the modulator block. You need to modulate this signal and then after that do the propagation. And then if you come back to take a look, the bandwidth here. This one you understand already, right? Bandwidth is inversely proportional to 1 over Ts, right? And okay, if 2 chips per 1 bit, so for example, here bit 1 represent by 1 and minus 1, right? Bit 0 represent by like minus 5. So actually is, okay, this is a code. Okay, what it means that bit 1 represents the chip of 1 minus 1, and if bit 0, it will be have the convert of the sign. Okay, it will be minus 1 and 1 for bit 0. And then if you take a look, the bandwidth of the direct sequence, it will be conversely proportional to the time duration of the chip. And the time duration of the chip equal Ts over 2, right? So here, this time duration will be what? Will be actually Ts equal to time of Tc, or Tc is TS over 2, right? And then if you want to find the bandwidth of the direct sequence, so you know that TC is equal TS divided by 2, or you move 2 up here, right? So you can see that actually bandwidth of the direct sequence is 2 times of the original bandwidth of the signal, okay? Then if I change the problem, I want to make wider band than 2, for example, I want to make it like very wide, 10 times. So what I have to do is what? I have to bring a code with 10 length of the code, right? 10 pulse of code to represent just only 1 bit. Okay, so 1 bit represent 10, I can say chips, okay? If 1 bit represent 10 chips, so it means that the bandwidth of the chips, or here of direct sequence space spectrum, become 10 times of the bandwidth of the original signal, right? So if you want to make it wider, you have to make 1 bit become like n chips, then you can achieve the bandwidth n times of the original signal. Okay, any question? So if I like to make it in general terms here. Okay, if the transmitted chip are n times narrower than the data bit, then the bandwidth of the signal is n times larger than traditional system. Okay, and then so that n can be considered or referred to as the bandwidth expansion factor. So if you make n chips, then the bandwidth become n times of the original signal. Okay, so sometimes we call n as the bandwidth expansion factor. All right, that is what transmitter do. And then for the receiver side, we do reversely. Okay, so after receive the signal, okay, do some amplification and then demodulate it, and then use a code to make a chip to be original data, right? So it just do the reverse process. Okay, and here is the block diagram called correlator. How can we detect after demodulate signal? Okay, after demodulate that signal, it can be like very small pulse. It depends on what code you use. And then how can we detect the original signal from here? It uses the hardware or the system called correlator to disperse the signal. Okay, it can be like this. The concept of correlator is to do the correlation. Correlation means that you compare two things. If it's very, very similar to each other, you are surely that these two are the same. So what it means in this direct sequence per spectrum term is that it compare this one after you demodulate the signal that you receive. Okay, you receive the signal. You receive the signal and then you do the demodulation, and then you get this one, this block that you already demodulate will be compared with the chip that you know before. Why do you know before? So this one, okay, this is the same thing that you have to know before at the transmitter side. So what is the code you use for map the data to be a chip? You use that code also. So you compare these two together. I mean the code that you use in transmitter side and what you just demodulate from the receiver side, And then you compare, you check, and actually in mathematical terms, you do the inner product. You understand the inner product, right? You do the inner product between two functions, and then if it's very similar to each other, if you compare like these two, you can like move a bit, and then if you check that these two is very similar, then when you multiply these two together, it will become the highest peak. Okay, if you compare to other part, you will have only one highest peak. Then you surely say that that one is the correct signal. Okay, that can be bit one, and so on. Yeah, this is a concept of correlation. You compare two things. If it's very close to each other, then the correlation function will give the highest peak to detect the original signal back. Okay. All right, this is an example of real application that uses a technique of direct sequence. It's used in Wi-Fi. Okay. This code is called Barker code with the length of 11. So this is N. Okay. So Barker code length 11 used in IEEE 802.11, which is Wi-Fi, as a spreading signal for the physical layer of the direct sequence given by here. This is the code. Okay. This code will representing for bit 1 in a binary communication. So this is a representation. This is bit 1, positive value. And then if you want to map this bit 1 into by using a Barker code, then you get a chip like this. Okay. So it can be 1, 1, 1, 1, 1, 1, 1, 1, and then minus 1, minus 1, minus 1, 1, minus 1, minus 1, 1, minus 1. So this one is here. All right. But if it bit 0 should be negative value of voltage, right? So it multiply here minus 1 with this code. So from positive value, it become the negative value, right? So it's just reverse of the sign. So it can be like minus, in this case, if this is 0, right? It can be, you can multiply minus 1 to here, and then it will be reverse of this one. Okay, and this is another example represent the data sequence. Say you have not only one bit duration, right? When you transmit a signal, it's kind of like a data sequence. You send the streaming of the signal, right? And then within this example, this is a data sequence in time domain. In time domain, it means that you represent this one by the x-axis represent time, and the y-axis represent the data voltage. Okay, so this is 1, 1, okay, 1, 1, minus 1, 1, minus 1, and capture here. Say maybe this one represent within 1 second. Capture only 1 second here. And then this data will be mapped using a code like this. Okay, this is a code. Then here is the output of the spreader, right? So you multiply the code for each bit. Okay, this is bit 1 represent how many length of the code. It will be 1, 2, 3, 4, 5, 6, 7, right? So for bit 1 represent minus 1, minus 1, minus 1, right? 1, 1, minus 1, 1. And continuing with bit 1, okay? And for bit 0 represent with the minus 1 voltage, you multiply the code with minus 1. So it will be just do the multiplication. It will be 1, 1, 1, minus, minus, plus, and then minus, right? Okay, and then you do this so on, and you use this for the input of modulation. Okay, so in this example, it given that the symbol rate be 5 symbol per second. What is the chip rate? You still remember symbol rate, right? Symbol rate means that in 1 second, how many symbol that you can send, right? So in this case, you send 1 bit per symbol, say binary transmission. So it means that in one, it mentioned here that 5 symbol per second, or actually here is 5 bit per second, right? 5 bit per second, 1, 2, 3, 4, 5. And then it asks you how many chips for 1 second. How many? Is that 7 per second? Is that correct? What is the chip rate? What is the chip rate? Help me. What is the chip rate? You there? Okay, I will ask you in a quiz if you don't understand here. Okay, so we cannot get the good score, all right? What is the chip rate? Huh? How many chips in 1 second for this example? Brooke? How many chips in 1 second? This is called chip rate. If nobody answer, I will still be here. How many chips in 1 second? No one? No one here? You just joined the class and your physical is not here.
I'm here. I'm not sure, so I don't know what to answer.
Okay, let's do it together. You understand, right? In this case, for 1 bit, we represent with the length of 7 code, 7 length of the code, right? So for example, here, 1 bit, you represent with the 0 house, or we say code. And then you can see easily here that there are 5 bits in 1 second, right? So for 1 bit, you have 7 chips, right? When you multiply the data with the code, we call it the chip. So in 1 TH, within 1 TH, you divide it into 7 TC. Is that correct? Right? So 1 TS equal 7 TC, right? And then it mentioned here that in this example, the symbol rate is 5 symbol per sec. So it asks you to find the chip rate. What is it? The chip rate will be what? The chip rate will be เท่าไหร่คะ In this 1 second, you have 5 bits, right? But 1 bit, you have 7 chips. So you multiply 7 to 5. So in total, 1 second, you can have what? How many chips?
35.
Yes, 75 chips per second. So this is called chip rate, okay? This is chip rate. So the chip rate means that how many chips can send in 1 second. Then if you take a look here, you can see that, okay, 1 bit represent with 7 chips. Then in 1 second, you transmit 5 bit, right? And then in total, in 1 second, you can send 35 chips. Okay, this is chip rate. How about, okay, you understand symbol duration, right? Symbol duration means that the time that you take when you send 1 symbol. If I ask you to find the chip, chip duration. This TC, this is chip duration. What is the chip duration? Chip duration means the time that you use to send one chip. So in here, this is TC, right? This is the time that you send one chip. So it means that what? If you know the chip rate already, then you can easily make a conversion, right? 1 over TC mean the chip rate, the chip duration, okay? The chip, sorry, this is chip duration represented by time, but RC here, that is the chip rate. So it's like inversely proportional to each other. So if I ask you to find chip duration, it's easy to calculate from 1 over 35 in second, right? Because in 1 second here, within 1 second here, you can count number of chips, so 75 chips. So how about this one? Just only send one chip. You can take only 1 over 25 second, right? And for how about chip duration? If you know that if you know the symbol rate is 5, then you can calculate TS from what? 1 over here represented by RS. RS means the symbol rate. Symbol rate is 5. So it means that by sending one symbol or one bit, you have to take what? 1 over 5 second, right? 0.2 second. Okay. Any question? This is, I think, simple for calculation. Okay, if no question, let's take a look advantages or pros and cons of direct sequence. All right, direct sequence is also anti-interference and resist to multipath fading. This is the advantage. This is similar objective of frequency hopping spread spectrum, right? We want to fight with the interference and multipath fading, and it works well. But based on the wide transmission bandwidth of direct sequence needs much higher sampling rates. You can underline this phrase. Because of what? You need much higher sampling rate and therefore more complex hardware implementation. It means sampling rate, if you go back to the concept of PCM, you have to do what? PCM is to convert the digital to be, analog to be a digital, right? To be a digital signal. And then the first step of the PCM is to do the sampling. If you remember Nyquist sampling, so you need to do at least 2 times of the frequency, maximum frequency of the signal, right? So if you compare this frequency between no direct sequence and with direct sequence, the frequency of the direct sequence is much larger, right? You see here, you compare between symbol rate and the chip rate. In this example, you use 7 length of the code to represent 1 bit. So it means that the frequency of the chip is 7 times of the frequency of the original signal. So when you represent here by using the sampling theorem, okay, you refer to previous example. If this is Fs, but if it's 7 times of Fs, okay. So by using much higher sampling is good in terms of you can get the very similar signal of the original one. But if you take a look in the complexity of implementing of the hardware, this is much complex because you need very high efficient hardware to make a higher sampling rate. Okay, this is the That's the reason why this is the cons of the direct sequence. Okay, you need higher sampling rates, so it means that more complex hardware implementation for direct sequence. All right, I think that's all for the theory, and this is just exercise to make you understand more. Okay, let's do it together. After this exercise, I will give you time like 15 minutes to do a quiz, and then take a break and come back to start with the RFID. Okay, so let's do it together, and if you have questions, you can ask. Okay. Considering 2 volt peak-to-peak digital signal in 1 second, the binary stream is 11001. Please be noted that this is binary stream, but when you send the data, you have to send it as the electrical signal. And it mentioned here that the amplitude represents 2 volt peak-to-peak. So it means that the maximum voltage will be what? +1, and minimum will be -1. So you have to imply from this statement that, okay, by sending bit 1, it will be 1 volt. Okay, you can draw here in the graph, following graph here. And then let's see. Okay, it mentioned here that where a positive pulse represent binary 1 and negative pulse represent binary 0. When the direct sequence is used for spreading the input data with the code of 4 bits length. So the code will be given like this, -1, -1, 1, 1. So this one, you have to imply that you will map the sequence of 1 into 4 smaller duration, like here should be. Is that correct? So this is original data here, right? So here, original data. And then you multiply 1 with the code. And then this is direct sequence pulse, which is the data sequence multiply the code sequence, which is -1, -1, 1, 1. So this is -1, -1, 1, 1, right? And then it mentioned again here that the negative pulse represent binary bit 0. So you imply that if bit 0, so it is in terms of voltage, it will be what? Negative pulse means the negative value of voltage. Volt will be represented by, so you have to multiply -1 with the code. Okay, so it will be, right? 1, 1, -1, -1, right? After spreading, the signal is then modulated with the carrier, having frequency of 20 Hertz. So 20 Hertz means that in 1 second, you have 20 cycles of sine wave. And the amplitude of the carrier is 1 volt peak-to-peak. 1 volt peak-to-peak of the sine wave, what does it mean? So from minimum and maximum here will be 1 volt. So it means that the maximum will be 0.5 and the minimum will be -0.5. Okay, this is a sine wave, 20 cycle in 1 second. And then it mentioned that modulating this sine wave using BPSK technique by using the constellation diagram here. So after you convert the data sequence to be a chip, the chip will be modulated using BPSK, using this constellation. Okay, represent bit 1 equal, represent phase 0. This is 0 degree and 80 degree. We can represent here also 1 volt and -1 volt. All right, okay, let's do it together. And it asks you to find the symbol rate. Okay, I ask you, what is the symbol rate of the input signal? Huh? What is the symbol rate? 5, because you can see that this is 11001, right? You observe in 1 second. So here is 5. 5. Oh, this is not symbol. This is not symbol rate. Nah. If symbol rate, it will be 5 symbol per second. But if the duration, it will be 1/5, right? 1/5, right? In the unit of second, because this is time duration. Okay, but if I ask you the symbol rate, mean how many symbol per 1 second, so you can easily say, okay, 5 per 1. Actually, this unit is symbol per second. Okay. The second one, what is the shift duration of this direct sequence? Shift duration. What is the shift duration? Huh?
Over 20.
1/20. Yes. Second. And the shift rate will be 20, right? Because of what? Because one data represent full length of the code, but you have 5 data bits in 1 second. So then finally in total, we have 5 times 4, meaning 20 chips. It should be chips per second. Okay, chip rate means how many chips in 1 second. And then it asks you to draw T signal in the following graphs. Here, capture in 1 second, and then the data mentioned that the data will be 2 volt peak to peak, 11001, right? 2 volt peak to peak. So here to here is 2 volt peak to peak, 11001. So this is the data, 11001. Because it's mentioned here very clear that the positive pulse or positive volt represent bit 1 and negative pulse represent bit 0. So if you draw like this is 1, and then if bit 0, if you draw like this, is wrong. Okay? Because of what? Bit 0 is not represented by 0 volt, right? It mentioned clearly that it is the 2 volt peak to peak. So it means that bit 0 will be represented by -1 volt of the signal. Okay. And then this is data times code. What is the code then? Code is minus, plus, plus. So it should be for separation of minus, plus, right? So I will show you like here, right? Okay, so for bit 1, it will turn to be minus, plus, and then this is the same, minus, plus. But for 0 bit, it will be converts, or actually this is multiplied with -1. So it should be plus, minus, right? It should be 1, -1. And you continue with bit 0. This is wrong. All right, it should be here, right? And if bit 1, it will be like this, right? Okay, we're done with the convert the data to be a chip. Okay, this is ready for modulation. And then it mentioned that you use a carrier with 1 volt peak to peak and have 20 hertz, right? So it means that in one cycle, you will have 20, in 1 second, you will have 20 cycle of sine wave. And then the amplitude will be minus, 0.5 and minus 0.5 because it's 1 volt peak to peak. Then the amplitude of the modulated signal will be 1 volt peak to peak also, because you have to do the multiplication also, right? Between the original data that you want to modulate and the amplitude of the sine wave, you have to multiply with each other. So for 1 multiply with 0.5 will be 0.5, right? Then, okay, let's do it together like only one symbol, okay? So you have to see this one when you modulate. You have to think every chip, you mod every chip. One chip in this case will represent 1 cycle, am I correct? Because here in 1 second, you have 20 chips, right? And for the modulation, you have 20 cycle also, right? So it means that 1 chip represent 1 cycle, right? So here you have to see what data come into the modulation. So this is -1. -1, you take a look at the constellation. -1 represent actually this phase, right? -1 represent 180 phase. So it means that it should be like this, right? This phase is 180, right? And then next chip is -1. So the phase still here, which is 180 degree also. And next chip will be 1. So if you take a look at the constellation here, 1 volt represent the phase of 0 degree. 0 degree. So you start with 0 degree here, right? And this is still 1. And you do in the same manner. So here it will be the same, right? You copy here and to be here also. Okay, and then you do until it lasts 1 second. So this one is what? This one is this one is the signal that you send into the air with the wider bandwidth compared to the original data sequence. Okay, so the concept is very similar to what you learned before, but the additional things that you learned today is that before you do the modulation, you have to map the original data to be a chip by using a code that pre-given to you. All right, any question? So if no, yeah, I think to check whether you understand, let's do this together and not together. Okay, let's do this and submit to Canvas. I give you 15 minutes, okay? And then take a break 5 minutes, then come back at 11 o'clock, okay? I will publish this as a quiz in Canvas and you do it and upload the file, right? But this one actually is very similar to what we did before in the previous exercise, but different modulation technique, okay? There are 2 modulation required. One is OK and one is BPSK, and use the same constellation of the exercise, previous exercise. Okay, any questions? No? Okay. All right. So, okay, I give you time, then I come back again 11 o'clock. Okay. Zoom. All right. Okay. Okay, continue. So actually the concept of RFID is from like to be the next step of using barcode. Actually, barcode is used a lot in our daily life, right? For example, I mean, especially to detect the products, or every product have a barcode, and then it easily for cashier to check out the product. Okay, and also the factory and also every stakeholder in the logistic can detect what is that product. Okay, so we use barcode for a long time already, but now today we think there are some limitation of barcodes as well. Okay, I will show you for next slide, but this is just to show you the standard of barcode in Thailand. I think we use UPC barcode because we have only one like not this continuity along this image, but there's another standard called RSS. Okay, we use this often to identify the product, but recently, like 10 years ago and up to now, we use 2D barcodes as well, but not to identify the product, but it's like to identify something, but not the product. So but anyway, we can apply to anything, but you know, when we apply QR code, we have to generate a lot, and maybe it will like still be useful for usually 1D barcode for just identify the product, but use 2D barcode to another application. And I think in Thailand we use QR codes. I mean the standard we use is QR code. Actually, is from Japan, Denso company, and this is a kind of 2D matrix. Okay, X and Y. We have the information of the dot, black and white dot, in 2-dimensional. And for data capacity, it's like this is a lot compared to other standard. Okay, and yeah, is if you compare to other, it's kind of high speed scan. You can use like a smartphone for scan QR code as well, and you can use other device that can detect QR codes as well. Okay, so the essential for barcode is like sufficient clear contrast, right? Because if it's not clear, it's like fade, is blur, we cannot detect or detect correctly. Okay, so the essential, adequate print contrast is essential for barcode. And then the digital image scanner is used to read the barcode. And this is just like to show how we can apply the barcode in the industry. So for example, the one product, okay, this one is just represent the company name. This is from Celestica company and manufacturers. That means sometimes one company have many plants, right? Then it can mention that, okay, from Celestica, but this plant, and you can trace from, maybe the production line, something like that, and the date, and who will be the supplier, and what is the quantity of this product, and so on. Okay, so it's like we can use it as an ID to identify the things that you need to observe. Okay, and then now we try to like use RFID instead of barcode, because by using barcode is good in terms of cost. It can use worldwide, but we have to scan like within line of sight. You understand line of sight already, right? So I think this big figure can show pros and cons. So for RFID, actually, it is used instead of barcode for since 1980s already. Because of what? Because the disadvantage of barcodes is that you need to use the digital scanner, right, to read. I mean, the digital image scanner to read just one by one barcode. So it takes some time if you have many plans. I mean, many box of things that attached with the barcode, right? You have to like scan one by one. But if you have RFID scanner, because we use radio frequency, is the wave, it can be, I mean, the product which is in the shadow regions or within the abstract code can be scanned as well. And you just scan only one time, and then you take whole stuff here. Okay, this is take shorter time compared to barcode. All right. See, you have to scan like when you buy things at 7-Eleven or at the retail, you go to Lotus and then you buy many things, right? You have to bring it to the cashier and then cashier just scan one by one. But in the very near future, I think the cashier is just, okay, put it in a basket and put that basket into RFID reader, and then the reader can read all things that is in the basket. All right. And you do not need to like open the box, because you can like the radio frequency or the wave can penetrate to the box just inside a big box like this. But for the barcode cannot, right? You have to see the black and white bar clearly. So you have to like open the box and scan one by one. And this is the comparison of the RFID and barcode. Okay, for data storage, barcode have very limited. So it just contain information of some, for example, is you can like calculate from the number under the barcode as well, and then you have to interpret that number to, for example, the company name or the plant's name or the production line's name, just that. But for RFID, there's a chip inside, a chip, smart chip inside. So you have a place to store data. I mean, you can store more than barcode, because for barcode we do not need the data storage, right? And for RFID, we do not need the line of sight, right? So we just let the wave do. And for barcode, it requires line of sight, as I mentioned. But if you compare the cost, of course, RFID is higher, but barcode is very low. And compare with the widespread of usage, of course, barcode used long time ago. It used in many places already. It's ubiquitous already. But RFID is just okay because it's costly, right? It's just used for like specific applications. And for robustness, okay, robustness means that how it is durable with the environment. If it's scratched, I mean, if barcode is scratched and then you cannot, or it like to have something like draw on the barcode, you cannot read it, right? So for robustness in that sense, it not works for barcode. But RFID, if it scratch a little bit, but you use a wave for propagation, so you can still use it. And for other RFID, since it is a wave, we as a human cannot read or we cannot see a radio wave, right? So in terms of human readable, RFID cannot work, right? We cannot see a wave, especially a radio wave. But for barcode, we see a width of a black and white bar, and also we see a number under the barcode. So then, when the scanner doesn't work, sometimes the cashier just type the number, right? And then calculate later on what is that. So it is okay by human readability. But for RFID tags are reusable. I mean, the tags or the thing that we use to identify can be reused or rewrite. Okay, and multiple reading ability, authentication and encryption. So it's better in terms of security compared to the barcode. Okay, so for the example, I think you guys have experience with this already. This stuff use RFID technology, okay, in tollways, in passport, even in our library. Even if you haven't go to the library in the university, right? So our university use a barcode, I mean not barcode, RFID to detect the usage of the book. Okay, it's used to identify the book. It's good. And okay, this is e-passport and e-BTS as a ticket, and then use a Visa card. They embed with the RFID also. Okay, so yeah, this is application, and I used to show you this slide already. This is the okay, give me times too high. Voting control. Okay, so this is the example. I really like this one. It's very applicable in the shops nowadays. So it used the RFID in the system of cashless. So we do not need to have a cash, so you can buy the stuff, and RFID can work with this application. Okay, so for the system architecture of RFID is very simple. There are only 3 components in the system. Okay, one is the tag. The tag is sometimes called transponder. And that one is the thing that is attached to the product like this. In Uniqlo shop, if you see the sticker right here, actually behind this sticker is the antenna inside. Okay, this is the antenna inside, and this is the chip inside also. Okay, so this is called a tag. Then this sock can be identified that this is for men, or how much is it? Like that is used for identify the ID. And the second component is called reader. Okay, sometimes it's referred to as interrogator. And actually, this is the one who read the ID from the tag. Okay, and then after the reader read the information or the ID from the tag, it will process later on by the processing unit or the computer. All right, so at only 3 components are needed in the RFID system. Okay, so this one, so you have a tag, it talk to each other. I mean, between tags and reader, it communicate using, it depends on the frequency, but usually if it takes like very near distance, it should be high frequency or about 13 megahertz, if I'm not wrong. Okay, high frequency, because in the shop, you have to bring the tag very close to the reader. Here is the reader, okay? And then the reader will connect to the processing unit or the computer. Okay, so it means that the reader read information, and then the calculation may be you pass the information to the computer and let it, like, what you want to know, if you want to know what causes it, so the computer will like trace the information from the database like that. Okay, so I did show you this one already. Okay, I think it around us already about this technology. And actually this one, it applicable to use in the warehouse as well, because a warehouse means you have to check the product and have to trace what factory or production line or all whole process. You have to track every stakeholder in logistics, right? So if you use barcode, it's kind of like you take a long time to check back or trace back. Then nowadays in warehouse management is often use the RFID instead of barcode, especially in the big pallet. Of course, some product inside may be a barcode, but if you want to check whole stuff here, where it from, you just like use RFID reader to read information from this tag attached to the pallet. Then you can know that, okay, every box here is from which company and where is to send from our cargo or the warehouse, like that. Okay. Sorry. And this is actually my expertise is about localization. My works, actually we used to try to use our FID to detect the location inside the building. You can imagine that we cannot see our location clearly. Sometimes we can see clear in very near windows because you can still see, I mean, your device can still communicate with the satellite, but it's often the case that if you like go shopping inside a department store or you are under the ground, like the subway, you cannot see, I mean, the device cannot communicate with the satellite for sure. So the technology for LBS, you know, LBS, right? Location-based system, try to use the IoT devices or using the wireless propagation technology to detect the device inside the building. And RFID is one of the modules used often for LBS. Okay, because maybe it's the cost not that expensive. Then you just like use one reader and to detect the tag, you can like have a reader act as a satellite. You can put the reader, many reader in one floor, for example, HM building, right? You spend time a lot in 6th floor. And then if you want to use RFID to detect your location, you may install the RFID reader, for example, in the corridor, left, right, and also in between, I mean, in front of the lift. And then you have the tag with you. If you go very close to the left side corridor, then you can have an application to show and navigate where you are, something like that. So the concept is very, very simple. We use the reference device or nodes instead of GPS inside the building to detect tags in this case. Okay, this is the application. And not only RFID for localization, I just want to let you imagine. If you do not want to install or implement the system, you can use the light. I think I used to explain a little bit about the light. You have a light already along, I mean, every building use a light for illumination, right? But you know, the light is the wave we call visible light. The light that you see when you turn on the light, you see the color of like light, orange or white, right? That is we call visible light. Visible light. So you can use that illumination light for communicate to your device as well. Okay, the light can act as an access point. Okay, so it means that you can use the light to be the access point. And if you have your mobile phone to detect the intensity of light. So when you move from room 505 and you move to 504, we have different lights. The light can act as an ID, right? And then it will detect you when you move. It will detect that, okay, you are close to light number 1, right? You are close to light number 2 and so on. So this is very interesting one if you apply in the indoor localization, or you can use Wi-Fi as well. because Wi-Fi is already there everywhere already. Okay, so we can use access point to be a GPS, and every smartphone or a portable device like a tablet or iPad have embedded with the Wi-Fi or Bluetooth already. Okay, what I'm going to say is that actually technology is there, including RFID, light, Wi-Fi, Bluetooth, and even wireless sensor network, say Zigbee. This one can be applied to like specific application. In this slide, okay, this all can be applied for LBS technology. And when you think about your project, when you propose your project to us, right? So you have to select which technology you can use. So this one, this is a kind of like available technology for you, but it's just you to select which one is the best for your project. All right. So okay, this is just explain that not only RFID, it can be other technology also to be applicable in IoT-based application. Okay, come back to RFID. So this 2-page of slide is just explain about the localization, but I think you can look around by yourself. I will go to the fundamental of RFID. This is the core concept of it. Okay, so it is not new technology, you know, it's happened long time ago, Second World War, to identify friend or foe for aircraft. Okay, and then about 2000, the year 2000, it used actually is found by MIT, the Auto ID Lab. Okay, Auto ID Lab actually happened to detect the product in the, you know, the Walmart adoption and the retails that have a big cargo inside. And then, yeah, they try to use the radio frequency instead of using just barcode. Okay, this is what I explained already about the system architectures. It's composed of tags, right? It's composed of reader, and inside the reader, there are 2 main components. Okay, I will explain later on. You know, because this is UHF, this is frequency. HF, UHF, this is radio frequency. Okay, then when it talk to each other, it talk about high frequency, right? This is high frequency, but actually data is not high frequency, right? Data is the ID. It can be like only a digit or a number, right? Then actually what you have to do is like convert signal within radio frequency terms into a very low frequency, or to say the number of the ID. Okay, so the way, I mean, the component inside the reader should at least consist of high frequency part, and also to detect the data back as an ID. Okay, and then after you get an ID, the computer and processing unit will further use this ID for application. And this is inside tag. The tag communicate with the reader using the wave, right? So it should have the antenna. This is the antenna to propagate a wave, right? So this is the antenna here. Also in your mobile phone, if you like open your case and then you will see this kind of copper. This is called microstrip antenna. Microstrip antenna. Okay, so it's kind of like a zebra light like this. Okay, and then this is the terminate part of the transceiver. But actually, you as an antenna have to send what? Have to send information from here. Information is stored inside the chip or the IC here. And then if you have IC, and then you have to have the bridge, right? To accompany your data to the antenna. So you have to have the connection here. It's called connection between IC and antenna. And the plate here, the kind of like paper is called substrate. Is a kind of material that's used for fabricate the antenna. Okay, so if you like if you are the telecommunication student, you will learn about this in detail, but this is not necessary for you as the CIE student. Okay, but anyway, you have an idea, okay, that the data is inside here in the chip, and then there are a bridge to accompany data, and then the antenna here will propagate the signal. All right, and here is the type of the tags. There are 3 types of the tag. One is called passive RFID tag. With this type, it does not have a transmitter and power source inside. You can see here that we do not need a battery, right? We do not need a battery, and you may confuse that how they can communicate with the reader then, right? And how it works, how it can like communicate to each other. So the concept is like when you use a passive tag, of course, there is no transmitter inside. It means that no electronics things or hardware about like to have the amplifier or to have a battery to feed the power to the electric inside. No need. Okay, so if no need this thing, the passive tag is very cheap because we do not need to have a like complex hardware. They use the signal received from the reader to power the IC. Okay, this is, you have to underline this one. So this kind of tag should get close to the reader. Like the reader will like turn on the power. As long as it has the power, it will like propagate the signal, and then the tag should be close to the reader, and then it's kind of like the tag will be awakened, or like the reader will wake up the tag to say that, okay, you are in our coverage area. Just wake up and send back your data to us, like that. Okay, they use the signal, they means the tag, use the signal received from the reader. Okay, the reader will have a power propagate along, and as the tag move close to the reader, okay, it will wake up, and then it will send the ID back. Okay, when it wake up, it will send the ID back to the reader. So this kind of communication should be very close. It's kind of short range communication. For application, you may think about, okay, for airport link ticket, you have a kind of coin, right? Plastic coin. That is a tag. Okay, and inside that one, there's no power. There's no a battery or even like button battery, no battery inside, right? It can be very small, but if you want to go through the gate, you have to put the tag to the reader very close, right? Because it makes sure that it can get the power from the reader. Okay, so for the passive tag, it is commonly used in cost-sensitive applications. So if you think about low-cost application, you can use the passive tag, because having no battery and no transmitter, this leads the passive tag very inexpensive or very cheap. And this is a kind of shape of the passive tag. Okay, is very low cost, very durable, no maintenance required. Okay, and the power comes from the field, the electromagnetic field, actually. Electromagnetic field of the reader. Another type of the RFID tag is called active tag. This is the things that make the distance longer. You do not need to put the tag near the reader, but you can have like maybe up to 10 meter. The RFID tag still can connect to the reader, but you need the battery inside. You need the transmitter inside. Okay. Active tags have their own transmitter and internal power source, in which is used to power up, usually not always but a battery, but it can be a battery from like using the solar cell or other sources. So it just say that by using the type of active tag, you have to have the battery. I mean, battery source inside. Okay, it can be AA battery, it can be another type of battery, but we have to have the battery. And it have to have the transmitter. Okay, it have to have the transmitter inside because we cannot just use electromagnetic wave because we need a longer distance. We require a longer distance of communication. So it will be better to have like amplifier inside, modulation inside. This thing composed to each other, it become a transmitter. So the tag, inside the tag, it have like electronics thing stuff here, and you should have the battery to feed the power to the electronic inside the tag. This is very, how to say, this is not that like far from our daily life. For me, for example, I have a active tag used to like access to my home. Okay, ในหมู่บ้าน we have like we have a door, automatic door, right, to open and let the people in the community in. We just put the active tag in front of the car, right? It's very small, it's like only 2 inches, and then it can communicate with the reader, which is kind of far. So you can imagine about the tollway as well. That is the same system. You just put the ETC, like ETC box, and inside ETC box, we have active tags. It communicates like quite far, right? But at least you have to have the internal power inside to feed the power for the transmitter. Okay, and there are 2 types of active RFID tag. Okay, one is called active tag transponder. This work in the similar way as the passive. It is woken up when it receives a signal from a reader. So it means that, okay, it will have to go close enough to like wake up itself, but from the reader. It woken up with when it receives signal from the reader. So it means that it in coverage range of the reader. So this help conserve battery life of the tag, okay, by sending its signal only when it is within the range of the reader. So when it's very far from the reader, it should go to the sleep mode, right? And if it go to the sleep mode, we can save the battery because we just sleep. We do not like send any information. So we can save battery a lot. So this technique we call active tag transponder. And the application is obvious for like tollway payment, as I mentioned before. When the car embedded with the active transponder approach or close to the toll booth, it is woken up and it receives the signal from the reader at the booth. Then it broadcasts its unique ID to the reader and the payment is collected. Okay, so just that. After that, it goes to the sleep mode. All right, and for the second one, this is called beacon. Beacon is an active RFID tag. It is used in what I call previously is LBS, or sometimes it's called real-time locating system. Real-time means that you have to turn on yourself every time. You need to like send your information all the time, right? So For beacon, it consumes lots of energy, but when you compare pro and con, it's okay to like send information all the time. So, okay, it is used in this application where the precise location of the assets needs to be tracked. Okay, in this TLS, a beacon emits a signal with its unique identifier at the preset interval. So it's like when you turn on, you as a beacon will send a signal like periodic time. So for example, you set like every 5 seconds, you will send your ID. Okay, you will send your ID every 5 seconds, and then whenever you are near for one reader, that reader will detect you, and then the reader can use your ID to find your location, like that. Okay, so it consumes more energy when you compare to using the active IFID tag as the transponder. All right, so this is kind of shape how it looks like. So it's like this, and you may have seen like it used as a key, a car key, you know. So when you close to your car, you can use just your IFID key to unlock your car, right? Okay, another types is that it is the semi-passive tag, or sometimes it's called battery assist passive tags. Okay, so it's in between passive and active. It uses battery to power the tag electronics, but also depends on the reflex signal for communication. So to conclude, semi-passive tag for short is that there is no transmitter inside, but it still needs a battery to power some part of electronic inside. So it have some electronic inside, but not full function of the hardware as a whole features of the transmitter. Okay, so it can provide longer distance compared to the passive tag, but anyway, it's not far. It is not too far because it still needs the electromagnetic wave from the reader to wake it up. You understand, right? So for the semi-passive, it works if it close to the reader because it needs the power from the reader, but at the same time, it needs a battery to feed the power for electronic inside. So the advantage compared to the passive is that it provides longer communication, but still not long, not too long. So it's like in between, and the price of is not that expensive compared to active tags. It's often used in the plant, in the factories, in the logistic for semi-passive, or sometimes it's called semi-active tags. This is example, all right? And this is a format of the tags. It can be like very, very thin, like a paper. It can print from the RFID print tag as well. It print, it can print the antenna, and it can be embedded with the chip later on. And nowadays, if you go to the airport, you can see that this label actually is embedded with the RFID, not barcode anymore in some country. All right. This is an example of the smart card, and this is used in, as I mentioned, in the warehouse or logistic. Okay, and this is a leader. Oh my God, we are out of time already. I will conclude just in between 5 minutes. For the reader, as I mentioned, there are two fundamental blocks. One is the control system, okay, and another one is the high frequency interface here. There are two main components. For the control system of the reader perform following function, it used to communicate with the application. So it means that after you have the ID, you send the ID to the application, and then you implement for further use of that ID. And the second is to control of the communication between transponder, like act as master and slave. Okay, because one reader have to take care or look after many tags, right? So it should have a control unit to do that. And it has a function of signal encoding, coding and decoding in this control system. And for the it's high frequency. Actually, this one is just like do like part of when you send information like a wave, right? A high frequency of the radio wave. And then HF interface means that this part will receive a high frequency from the tag. Okay, so high frequency will connect to the antenna to receive information from the tag. And then after that, it will demodulate the information from high frequency to be a lower frequency and further sent to the control unit. Okay, this is a card reader you can like observe in somewhere in daily life. And how ID system work, it's very simple. Like this, you have transponder or the tag. Okay, and you have a reader here. Both have antenna, right? When a transponder or a tag is in the communication range, close enough to like communicate to each other, its data is captured by the reader. The data means that it captures in radio frequency format for the signal, and then can be transferred to the standard interface to host computer. Okay, this is RF module as you compare to here. It is a HF interface, and this is a control module. And then the data from control module will connect to the computer. Mostly use a cable of RS232 or maybe update. I'm not sure, you can check later. It can use maybe other cable type. Just that, okay? It's work very like similar way with other wireless signal work. So it means that from data ID, you need to modulate with the carrier, and send using the antenna. So for the receiving side or the reader, so it like demod and then get an ID and then send to the host computer for make an application. Okay. All right, I think it's just that. So this is just show the range and frequency available in the market. It depends on the frequency used. If very high frequency like ultra wideband in gigahertz frequency, it can up to 10 meter. But if you use a tag like to access to your dorm, for example, the range is very short, maybe shorter than 10 centimeter. Okay, so you can check the characteristic and the performance used in this table. Yeah, I think that's all for my lectures today. Okay, I think you can review by watching my clips of lecture later on. Okay, it's time for lunch already. Any question? If no, let's meet again next Thursday. And I think Ajahn Sumek need to know your progress on the project. And unfortunately, I am not available next Friday, so it can be the second session of Thursday, say maybe 11 o'clock for project progress presentation. But I will confirm you again after I finalize with Ajahn Sumek,นะคะ. But anyway, we still start the class from 9:30. on next Thursday. Okay. All right. Any?
Do we have class tomorrow ครับ
No class tomorrow ค่ะ Let's do your project นะคะ
โอเคครับ
Thank you